Hello, this is Mr. Antrim. This Chemcast is on thermochemistry. It involves finding changes in enthalpy, delta H, by using bond energies. As you recall, we have already studied how to find delta H by methods such as calorimetry, Hess's law, and also finding delta H by using heats of formation. In this tutorial, we are looking at how to use bond energies to find delta H. So, if you recall, in a chemical reaction, of course, chemical reactions take place when bonds are broken and new bonds are formed, and this results in new combinations of atoms. Of course, we call those chemical reactions. One thing you must realize that it always takes energy to break a bond. That's an endothermic process. Bonds represent stability, so it takes energy to break them. Conversely, when bonds are formed, energy is released because bonds represent lower energy states and more stability. So breaking bonds costs energy, forming bonds releases energy. So to use bond energies to find delta H, we will rely on this equation, which says that the delta H is equal to the total energy involved in breaking bonds minus the total amount of energy that is produced when the new bonds in the products are formed. Bond energy is simply, again, the value of energy, generally measured in kilojoules per mole, for breaking or forming a bond. An example, the carbon-hydrogen bond in methane has a bond energy of 413 kilojoules per mole. There are charts in your textbook that provide this data. Of course, in methane there are 4 CH bonds, so it would take 4 times that amount of energy to completely break the bonds in 1 mole of methane. There's an example of a table that we would find in our textbook. You can see the hydrogen-hydrogen bond has an energy of 436 kilojoules, so 436 kilojoules would be required to break that bond, or we could say that amount of energy would be produced when a hydrogen-hydrogen bond is formed. We can see some bonds have fairly high bond energies, some are lower. So this is a useful chart that you'll use in doing certain calculations. Notice the carbon-carbon multiple bonds. Triple bond has more energy than the double bond, and this triple bonds simply have more energy than double bonds, 835 to 611. You might recall that from our study of chemical bonding. You also might recall from first-year chemistry equation or graphs such as this that represent the progress of a chemical reaction. If the reactants, for example, have a given amount of energy donated on the y-axis, chemical reaction takes place. There's an activation energy involved. We'll study that later in our chemistry when we get into the topic of kinetics. But the energy, after the activation energy is met, then we produce products. And in this case, you can see the products have less energy than the reactants, and this represents the delta H. An exothermic reaction, such as the combustion of methane, producing carbon dioxide and water. In this graphic, we see that the reactants, the methane and oxygen, have collectively this amount of energy. It requires some energy to break bonds, so now we have just carbon atoms, individual hydrogen atoms, and at one point individual oxygen atoms, because the O2 molecule must have been broken as well. Well, it turns out when the new bonds are formed in production of the carbon dioxide and the water, the total bond energy here is less than what we started with, so it turns out since we have less energy in the bonds, then that energy was released to the environment, and this would be an exothermic reaction. On the other hand, in this reaction, we see that the reactants start out with collectively this amount of energy. We have to break bonds. In this case, once again, when bonds are formed, we always get energy out. But in this case, we got less energy released when the new bonds are formed than what it cost to form to break the original bonds. So in this case, it's an endothermic process because we had to add energy to the system in order to create this or cause this reaction to occur. So let's look at a specific example, putting some numbers to this. In this case, we have to break 4 CH bonds, and we also have to break 2 oxygen-oxygen double bonds. So we look up this information, look up the values, plug those in, and we find it takes this amount of energy to break the bonds in this chemical reaction. When the new bonds are formed, we form 4 oxygen-hydrogen bonds. Remember, there's obviously 2 hydrogen-oxygen bonds in every water molecule, but we have 2 moles of water, so it's a total of 4 moles of oxygen-hydrogen bonds, and we're going to produce 2 CO bonds because in each carbon dioxide there are 2 CO double bonds. So we plug those values in. Again, we'd have to look up these values for the bond energy of an OH bond and a bond energy for a CO double bond. And we see that it takes this much energy would be released when the new bonds are formed. So we plug those into our equation, and we get a total of negative 818 kilojoules per mole. So this means that this is an exothermic reaction. So bonds broken cost less energy than what it took to form the new ones. So energy was released to the environment in an exothermic reaction. Of course, methane, natural gas, is a very important source of energy to heat water in homes and so forth. If you don't remember this particular reaction, and I don't think it's given on the AP equation sheet, you don't really need it. All you have to remember is how to tally up, do the little bond inventory, tally up the amount of energy to break bonds, the amount of energy released when new bonds are formed. Then if you didn't remember which way this went, you can reason your way through it, and just as long as you know that it takes energy for this process and energy is released for this process of breaking bonds. And then you just look at it and say, well, I'm getting more energy out than what I put in, so I know that's exothermic, so I know the value is going to be a negative. So again, you don't have to rely on that particular equation. Our last example, let's look at a problem of the formation of a molecule isopropyl alcohol from the reaction of acetone and hydrogen. Well, this is an organic reaction. There's the equation. The problem, if you were only given this information, you don't exactly know, just by looking at the molecular formula, how these atoms are arranged, and in particular what combination. And the same is true for the isopropyl alcohol molecule. So actually, you have to look at the Lewis structures. That's why in your textbook, this concept of bond energies for finding delta H is not presented until chapter 8 in the chapter on chemical bonding. But since we already know how to do Lewis structures, or in this case, you can be given the Lewis structure. And this is the acetone molecule, the hydrogen molecule, and here's the product, the isopropyl alcohol. So now we can see specifically what bonds are involved. And again, we couldn't quite tell that from here. So we need to sometimes, particularly in organic chemistry, know the Lewis structures before we can do the bond accounting. So here's the reaction again with Lewis structures. And if you look at this, you can see there's a CO double bond here, but there's no CO double bond in the products. Therefore, I know I have to break that. There's this HH bond here. There's no HH bonds here, so I know that bond has to be broken. And we can also look at these bonds. There's 6 carbon-hydrogen bonds. But over here, there's also 6 carbon-hydrogen bonds, so we really don't have to concern ourselves with those. They're not broken in this process. So we look up the values for the carbon-oxygen double bond and the hydrogen bond. So it tells us it would cost us this amount of energy to break those bonds. When we form the bonds, we notice that there are 3 new bonds. There's a hydrogen-oxygen bond that didn't exist before. There's a carbon-hydrogen bond that did not exist before. And there's a carbon-oxygen bond that wasn't in the reactants. So all those new bonds are going to be formed, and when bonds formed, energy is released. We look up the values, plug those in, and we see it takes, we would get 1,220 kilojoules out. Once again, if you didn't recall the equation at this point, you can just say, well, this is what it's costing, this is what I'm getting out more. So once again, it's an exothermic reaction. So ultimately then, you could use the equation, plug it in, and we get a value of -39 kilojoules per mole for this particular reaction. So this is an example of how to use bond energies to calculate enthalpies of a reaction. And you should now be able to do these problems that are assigned from the textbook and the worksheet.